Dear colleagues, my name is Patrizio Ansalone and I am a researcher at Istituto Nazionale di Ricerca Metrologica. First of all, let me say thanks to the organizer of Trending Magnetism for giving me the opportunity to present this talk today entitled Magnetization, Transport and Local Exchange Invariance. Let me start from the synopsis of this talk. The first step would be the quantum iron-on-Kasher effect, and the second one, the classical analogous of the spin wave interacting with an electric field. I suggest to see the talk by Vittorio Basso, Electric Field Effect on Spin Wave and Spin Currents. In order to generalize the previous results, I will consider the cosset space, then the global and local rotation invariance, and the introduction of a gauge covariant derivative. We need these three fundamental steps to define a gauged exchange magnetic energy and a topological phase. Then I will highlight two results: the Luchisky-Maria-like interaction, which is obtained in this program for free, and a topological phase. As I said before, I would like to introduce the iron-on-Kasher effect, which is well known in particle physics, especially if you consider a particle such as a neutron, which is a neutral charge with an intrinsic spin. From the physical point of view, you can consider the full space, and the particle moves in a region which is free of charges, but there is another part of the space which is inaccessible because the presence of an infinite line of charges which generate an electric field configuration which is radial and static. In this situation, if you consider double-slit experiments, the Schrödinger wave function acquire a phase, and this phase can be measured in an experiment such as neutron interferometry. And the phase, it has the following expression by the integral over a closed path. It depends directly on the electric field and the magnetic dipole, and it is a quantum effect. Then, just to recall some aspects from the dynamical point of view, such a kind of particle transport momentum. The momentum has two contributions. The first one is the mechanical ones, and the second one is the cross product between the electric field E and the magnetic dipole mu. And the phase, as I told you before, is exactly an integral between 2 points or alternative along the closed path. And this phenomenon is well known as iron-on-Kasher effect. The point, one of the points is that is there something similar in a classical situation? For example, if we consider a spin wave propagate along the y direction under the effect of the electric field E, it's possible to measure an accumulated phase. The answer is yes, and we obtained the results in this previous paper, you can see at the bottom. And the phase can be computed in the same, with the same analogous relation that I showed before. Taking account this coefficient, gamma L, which is the gyromagnetic ratio, and the inverse squared of the speed of light. From the physical point of view, the effect is that the dispersion relation translates according to a specific amount, which is proportional to the electric field X, coupled to the coefficients that I told you before. So this is a particular case because the magnetization in this case is described by a spin wave, which is an approximation. And then what I would like to highlight in this situation is that the transverse electric field causes a shift of the dispersion relation on the spin waves. In the k-vector space is simple because it is a translation of the ky vector, but if you consider the same expression in the coordinate space, it's equivalent to redefine the partial derivative. So the partial derivative can be substituted in the well-known exchange energy, and it is possible to obtain a new one. And it contains three different terms. The first one is the well-known exchange term. The second one is the Dialogowski-Moria-like interactions, and the last one is an easy plane anisotropy. So this is the results on this approximation. Further, we want to know if it's possible to generalize to a case where we consider not just an approximation or a specific case just spin waves, but we want to study a generic configuration of the magnetization vector. So, for doing this, we need to sum geometrization concept regarding the macromagnetic description. The first step would be the introduction of the invariant gauge formulation of the macromagnetic energy. At a more fundamental level, we need to introduce a non-abelian gauge covariant derivative in order to obtain an exchange energy, macromagnetic energy, invariant under a gauge transformation. There are two advantages regarding this method. The first one is that we can use the field theoretical machinery, and the second one, we can use the group theoretical approach in order to understand the symmetry in the system under study. So in this case, it's possible to generalize our first result. So the coset space is the space defined in this way. Is the Cartesian product about the sphere S2, which is the space where Lie, the magnetization. In fact, the modulus of magnetization is constant, so you can consider a point Lie on the surface, the spherical surface, and the vector M is invariant under a rotation around its own axis. In fact, if you rotate the magnetization of an angle psi, the vector is the same. So the Cartesian product of the two space define the Lie group SO3, which is also manifold. This Lie group is simply the group of the rotation three-dimensional space, and it is non-abelian in the sense that if you it's not commutative, because if you apply two rotation matrices on a vector M, the result is different if you apply in a different order. So let me introduce the global and local rotation. Generally, you can consider a standard XY reference frame on the plane, and you can attach at each point in the R2 plane in each point, but you can do other choice. The first one on the right is the global rotation, where you can rotate the reference frame in each point of a fixed angle. Or in alternative, you can do a local rotation, meaning that you can attach at each point a reference frame, but the point you defined contain a reference frame dependent from an angle point by point. So, from a pictorial point of view, decide to define a reference frame. We attach on the curve geometry because the geometry of the system or the geometry induced by electromagnetic field, and then you can choose an arbitrary orientation of the system. But which are the consequences of this arbitrariness? The first point is the covariant gauge derivative. The starting point of a gauge invariant description of the macromagnetic energy is the introduction of a gauge transformation acting defined by the matrix R, acting on the vector magnetization M. In general, both in Landau fields in Brown, for example, in magnet-elastic interaction, the macromagnetic energy is invariant under a rotation, global rotation. But if you promote this rotation to a local one, according to the previous definition, the macromagnetic energy is no longer invariant. You have to solve this problem. by requiring that the covariant derivative transforms in a covariant way. So this is simple, but there's not enough time to enter in detail. But introducing the gauge covariant derivative, it means that you need to modify the partial derivative, standard partial derivative with an emergent gauge field. This emergent gauge field is a way to compensate the effect introduced by the rotation point by point. And also the vector potential A prime mu, the emergent gauge potential, has a special change of structure when you act with a rotation. Why we introduce this structure? This structure is the fundamental point, because we can introduce exactly the same the covariant derivative for the space, for the coset space that I introduced at the beginning. The gauge covariant derivative is defined in two pieces. The first one is the partial derivative of the vector m, and the second one is the cross product between the magnetization vector m and the partial derivative of the vector psi, the angle that I defined before. And by assuming that the second piece is directly related to the electric field and the magnetization m with this tensor structure, it's possible to express the gauge covariant derivative in terms of the electric field and the magnetic field. There are two pieces. In orange, the part which depends directly on the electric field and magnetization, and the other one, the classical partial derivative. And why it's so relevant, this definition? Because in this case it is possible to generalize the macromagnetic energy. In fact, the macromagnetic energy density for a ferromagnet interacting with an electric field is transformed upon a formal redefinition of the standard partial derivative, because the introduction of a gauge theory is exactly the reason and the method that it uses in theoretical physics in order to introduce the interaction between two fields. In this case, the magnetization and the electromagnetic field. So, the general structure of the new macromagnetic generalized energy contains two terms. The first one is always the well-known exchange macromagnetic terms with the stiffness A. The second one, in red, is terms like the Delaczewski-Moria interaction in a general case, and in blue, the anisotropy terms. Moreover, as I said before, just to let me back here, I decided it's relevant to highlight that I prime mu contains two terms, but I'd like to reduce the case when only the second one exists, which is called the pure gauge, which is the partial derivative of the matrix R multiplied by the inverse of the matrix R, which is in this case the simplest, the transpose of the matrix. So, in this case, it's possible to introduce a topological phase, which is defined by the cross product between the pure gauge potential A alpha and integrate over a loop. So, it's possible to prove exactly that it's an integer, and it is the analogous of the case where the case were shown at the beginning for the spillways, but in the general formulation. So, summarizing our results, it's important to recall that in this background we have obtained the Delaczewski-Moria-like interaction for free, just to introduce a gauge covariant derivative in the abelian and non-abelian case. We have obtained the topological phase as results, and you can see some detail in this paper. And take home message: In an invariant gauge formulation, the magnetic energy density of a ferromagnet interacting with an electric field is transformed into nu upon a formal redefinition of the standard partial derivative, which is the key point for all gauge theory. Describe the interaction, modifying the partial derivative. So, if there are some questions, are welcome, and thank you for your attention.